Hi everyone. So up to this point we've been talking about a bunch of different kinds of energy, and I said that as we start to learn more of these types, we'll just keep tacking them on to the conservation of energy equation. So the next one that we're going to look at is elastic potential energy. Now you're probably familiar with that. Anything that's stretchy is going to have some sort of elastic potential energy. A spring is the obvious one. Any actual piece of rubber band, a bungee cord, any of that. In the case of a spring, it's not just stretching, it's also could compress. We're still storing energy when we compress that. This actually applies to almost every material, particularly if you're an engineer, if you're a mechanical engineer, material science, then you could take a bar of steel and it can actually be compressed, and so it will store energy in that way that it can then be released, and this is something that you would have to deal with. So elastic potential energy is very common and very important. So while we are going to derive the equation for the elastic potential energy, up to this point we've strictly been looking at the units. Now we need to think about, well, how do I determine if something's supposed to be squared or to the third power or to the fourth power square root or anything like that? That's something that can be hard to tell from the units with this. So particularly when we've got a quantity that we just don't know exactly what it is. So what we're going to learn today is how we can take our data that we've taken from the real world, and we're going to look at the curve from that data, and we're going to interpret what kind of curve that is. In your book, you've got kind of a library of different kinds of curves. You've got linear curves, you've got quadratic curves, anything like that. Now, we could put this in Excel, we could put this in the data graphing program, and it'll do a curve fit. But sometimes you have to know, wait, which curve fit am I looking for? Am I trying to get, is this data supposed to be linear? Is its data supposed to be quadratic? When you get into engineering, though, into doing real world engineering, as I mentioned last time, you're going to have this polynomial that has a whole bunch of coefficients in it, and the powers might be very strange powers that come about with this. So you might have something raised to the 2.25 or something. So learning to recognize the basic curves will help you when you're trying to interpret those data. So what we're going to do then is we'll come up with our equation just using the units. Then we'll take some data, which I'm going to have you actually plot in your book, and then we'll use that to determine whether something should be raised to a power or if it's linear or whatever. All right, let's get started. Okay, so as always, so this is microtask one. Our first task is to figure out what do we think this depends upon. So remember, it's a potential energy, so it's stored energy. Let's consider a spring. That's probably the easiest thing for us to look at, but remember that this applies to anything that's going to stretch or compress. So let's say we've got a spring, and think about what quantities might determine how much energy is stored in that spring. Think of all the springs that you've ever had to deal with. There are many different types, and they responded very differently. So pause the video, brainstorm a little bit, and let's see what you can do. It's going to be real important you pause the video in this one so that we can build that understanding that you need. Okay, so a couple of things you might have thought about. Certainly, if you think about if you stretch that spring farther, there's going to be more energy. Same thing if you think about a spring cannon on a robot. We compress this. Now I've got all that energy stored. When I release that, all that energy gets converted into kinetic energy, and that's what's going to kill your enemy bot. But the more I compress it, the more that energy that I'm actually storing in that. So we can probably say that the compression distance, and let's make ourselves a symbol here. And I'm going to say compression, but it can also be stretching, right? Just depends on which way you want to go. I'm going to say compression just because that's what we use with the robot, with the spring cannon. Whoops, I don't want to I want the compression distance. All right, and we need to define a symbol for that. Well, okay, it is a distance, right? So it's going to have units of length. It's going to have units of meters. So we could think about maybe using x, but that doesn't necessarily talk about a compression. Remember, compression has got to be a change in something. So in this case, really, probably a better symbol would be to say delta x. And it's going to be a vector because it matters the compression distance, if it's actually the distance is getting smaller, well, then it should be negative, right? On the other hand, if it's getting bigger, well, then it should be positive. And as we always know, delta means change in, so this is equivalently our final position minus our initial position. Okay. So in the case of springs, we will often, and where this xi is, we'll often talk about when the spring is just sitting there, when nothing's compressing it, nothing's stretching it. And so that just becomes its rest position. We call that its equilibrium position. And so we'll use the x0 as its equilibrium position. And then my change will be from that equilibrium position, whether I'm stretching it or compressing it. For now, let's leave in the xi, and let's see where that gets us. All right, so what other things can you think about that would affect how much energy you can store in the spring? And equivalently, you can think about it, what else can I think about that would cause that spring to launch the projectile a lot faster, give it more kinetic energy? Well, if you think about it, there are different kinds of springs. A spring that's on, say, a railroad car is very stiff, right? It takes a lot of pressure to get that thing to compress. But then once it does, then wow, we get all that back and we can really launch things a long way. On the other hand, the spring in a ballpoint pen or something is quite flimsy. And so the stiffness of it is really, really low. A slinky, if you ever played with one of those, it's a spring, but the weight of the slinky actually exceeds its stiffness so that it doesn't restore itself very well. It'll sit there and vibrate, but it probably won't come all the way back up. So somehow we need to talk about the stiffness of the spring. And remember that that could be for elastic, it could be for the spring. In the case of metal, for example, we've talked about how that's going to have, you can stretch or compress that. That stiffness is going to be extremely high from that. It's going to take a lot of force to get those things to come together. Okay. Now we're going to need some sort of a symbol to represent that stiffness. We'll talk about this in a little bit, but for now, let's just assume that it's some constant. So it's some constant of the spring. We don't know what it is. We don't know what units it has. But we do know that it's fixed for that particular spring. Okay. So one of the other things that we have to think about when we're doing this is with a real spring, you've probably noticed that if I stretch it too far, then it doesn't come back to its original limit. And so that's the range at which we get most of the energy back. We call that its elastic range. And the maximum stretch or compress we can do for that, at which point that it now just changes the stiffness of the spring, that's called the elastic limit. If I am within the elastic range, then we can consider the energy that we store in it to be reversible. It's a true potential energy. It's not a dissipative loss. So, and that's important because now, as long as I'm in that elastic range, I can squeeze that. I've got energy stored. I'm going to get all that out when I launch my projectile. On the other hand, let's say I had a really, really stiff spring and I compressed it to the point where I bent the spring. I bent the coil in the spring. Well, at that point, some of the energy that I tried to put into it went into rearranging the molecules. It was deformation energy, which means I no longer have as much energy stored in that spring. So we're going to assume for all of our discussion that we're within the elastic range of that spring for now, just to make sure that we're keeping it all nice and simple. All right, let's take a look at the next page. Okay, so we want to design an experiment that's going to allow us to measure the energy contained in the spring. We know that it is reversible, so therefore we know that any energy that goes in will come out. So pause the video, brainstorm for a minute, see if you can come up with an experiment that would allow you to measure the amount of energy stored in that spring. I mean, there's no instrument that I could use that would do that. So what could I do? Take a minute, pause the video, let's see what you come up with. Are you just waiting for me to give you some ideas? You really need to do this on your own. All right, so there's a couple of things that you could try, and pretty much all of them will work. So, for example, we might have, let's say, I've got my robot, and let's say he's got some sort of a spring attached to him. We'll do it like this, all right? And it's attached to the wall. So then I could put an ultrasonic sensor, which looks like kind of robot eyes on this. If we compress the spring, now there's some energy stored in that. As soon as I release it, what's going to happen to that energy? Where's it going to go? It's reversible. as long as we're within the elastic range of the spring, it's reversible. So we're going to get all that energy out. Where's it going to go? It's going to go into kinetic energy for the robot. So we use this symbol US for the elastic potential energy because it's a spring. We don't use an E, by the way, because eventually we're going to talk about the electromagnetic stored energy. So we'll go there later. All right, so I'm converting my spring energy into kinetic energy. And you say, yeah, that's a really easy way to do it because I don't have any changes in velocity. I'm sorry, I don't have any changes in potential energy because I'm on a level surface the whole time. Friction is probably there, but it's also probably small as long as we're sure that our wheels are freely rolling, so it's not a bad idea. So if I were going to write an equation for that, then I would say, all right, I've got a spring and my robot has maybe some initial kinetic energy. We're going to see that it doesn't. And then I'll have this, right? So always write out this conservation of energy equation. Then go and mark out everything that's zero. So for example, initially when I first compress the spring, the robot isn't moving. So does it have any kinetic energy? Nah. So that's going to be zero. I want to know the velocity the instant that it leaves the spring, because if there are no dissipative forces like friction or whatever, that's going to be the velocity it's going to have constant because gravity's not a factor here, is it? So at that point, my spring energy has gone to zero. And so I'm simply left with USI, which we'll just call the spring energy that's stored, is equal to the kinetic energy that I get out. So I can measure the amount of spring energy that I get by simply measuring the velocity, assuming I know the mass. Right? Now, the equation for this is not US, right? What I'm actually measuring against, I'm going to run a bunch of different compressions. So I'm going to compress a little bit, see how much energy I get. I'm going to compress a little more, see how much energy I get. This is nothing more, the kinetic energy here is nothing more than a meter. It's a tool for measuring it. I'm not saying that US equals 1/2 mv squared. That would be ridiculous, right? The spring isn't moving when it's there. It's got potential energy stored into it. But we decided that it must depend upon the spring displacement and the stiffness. All right, so now let's think about that. Let's start building our equation. So we want to come up with an equation for this. And we know it has something to do with the stiffness. Ask yourself, is it directly proportional or is it inversely proportional? Well, as I compress it more, we've got more energy stored. So that's going to be directly proportional. So we know that goes in the numerator. The next thing we want to ask ourselves is, what about this stiffness, this K? If we want a high number, high K, to represent a very large stiff spring, a very stiff spring, then as the stiffness goes up, what happens to the energy stored in it? That's also going to go up. So that's also directly proportional. So I know that I should have a K here. So far, I know it should depend upon these two things. And remember, there is always a constant here. We don't know what it is yet, and it might just be 1. But we know that there's a constant in there somewhere. What we don't know is, are these things raised to any kinds of a power? And there's no way that we can figure that out because we don't know the units of this constant. So I can't even use dimensional analysis. I mean, I know that the energy, remember from last time, is kilogram meters per second squared. So this K, if this is in meters, this K has to have units of kilogram meters per second squared. But what is that? That doesn't make any sense, right? So if I've got it the way I've got it right here, I honestly cannot tell what that expression is going to be. So for example, what if this were actually squared maybe? Then now I've got meters squared, and so K is just going to be this, because kilograms times second squared, kilograms divided by second squared times a meter squared is going to give me that. On the other hand, what if it were to the third power? Well, now that means I'm going to have another meter down here, right? That will give me kilogram meters per second squared times meters to the third will leave me with kilogram meters squared per second squared, and so it'll give me what I need. So any one of these units with the constant is possible, and there's nothing we can do to get that other than do an experiment. So what we're going to do is we want to experiment with each one of these individually. So here we can vary that delta x and then measure the velocity, and that tells us how much energy was in the spring. Even though I don't have an equation for it yet, I can measure it because I know that it's got to be equal to the final energy there. Does that make sense? So then what I would do is I might say, okay, for a bunch of different delta x's, here's the, whoops, not ek, we want us, even though they're the same, right? Let's be very careful about it. And then I could figure out, okay, is it linear, is it quadratic, whatever. So that's certainly one approach that we could do. Now, the only problem with this approach is, and it's not a big problem, but is that the velocity can actually be quite hard to measure. Remember that the robot has no way of measuring velocity directly. It can only measure the distance. And so I would have to go in and do an x versus t curve. So because I'm applying my distance versus time, and then use the slope of that to get the velocity. So it can be done, but it can't be done directly. So one other idea that you might have, what if, and I'll just draw it up here, what if I had a spring cannon and it was pointed straight up? So here's my spring. It's attached to the bottom here. And I take my projectile and I compress the spring by this amount delta x. What's going to happen as soon as I release it? Where is that spring potential energy going to go? It's going to go in the ball. But what's going to happen to the projectile? It's going to get some kinetic energy. Now you probably said, well, it's going to go up, and you're right. But let's start thinking about it in terms of energy. It's got some kinetic energy in this direction. Well, you may think, well, no, you're no better off. You still have to measure that velocity, right? We still got to find some way to measure that velocity. However, there's something different about this case. Eventually, the velocity, there's going to be a point where that velocity is equal to 0. What is that point? What do we call that? That's the apogee. So my velocity at apogee equals 0. So what is my kinetic energy at apogee? Well, at that point, my kinetic energy equals 0. Well, where did all that energy go? Think about it. Energy can't disappear. We start out with some spring energy, we converted that into kinetic energy, and then as the ball went up, it was going slower and slower and slower. So it was losing kinetic energy until finally it has no kinetic energy. Its velocity is 0. Where did all that extra energy go? It went into gravitational potential energy. So all of the energy at this point is in gravitational potential energy. So let's write our expression then. So I'm going to write it between here and here. So our initial, we're going to have USI plus UGI plus EKI equals USF plus UGF plus EKF. All right? And I'm not thinking about which ones are zeros yet. I'm just saying, okay, I know I've got a spring, and I know I've got gravity that's coming into play, and I know I've got kinetic energy. So I'm just going to write all these down. Now, initially, if I bring that ball all the way down to the ground, say I compress it all the way down to the ground, and I can actually set my 0 to be anywhere I want for potential energy. But let's say I bring it all the way down to the ground. Do I have any spring energy stored in there? Well, sure, I've got a lot, right? Do I have any gravitational potential energy if it's all the way down at the bottom? No, right? Because I'm on the ground. Is the ball moving while it's down here? Nope, so it doesn't have any kinetic energy. So all of my energy is stored in the spring. That's good. That's what I want. When I get up to apogee here, this is my final. Do I have any spring energy stored? No, the spring's already back up to its equilibrium position. So it's unloaded. All of its energy is gone. Do I have some gravitational potential energy? Sure, we just said that we did. That was it right here, right? Do I have any kinetic energy at that point? Interestingly, no, because that's where all of my kinetic energy has been converted 100% into gravitational potential energy. So you see, doing this kind of analysis, it's a lot easier than jumping right into a bunch of algebra from that. I can look at this and say, oh yeah, only thing I have initially is spring energy, and look at that. I don't actually need the kinetic energy to solve this because it was 0 at both the places. Now, if I had chosen anywhere in the middle, I would have both UGF and EKF. And so then I'm going to have a velocity, or measure the height, or something, or both, in order to be able to do this. So here I'm left with my spring energy is equal to UGF, which we can now say my spring energy is equal to mgh. So I now have another way with this experiment to measure. All I need to do, assuming I know the mass of the projectile, all I need to do is see how high it went. And that's pretty easy. Take a big 2-meter stick and then take a camera, take your video camera, and record it going up. And then just go frame by frame and then read off next to the meter stick how high this thing went. In lab, you'll be doing something very similar. You'll have an actual cannon, you're going to shoot things up, and you're going to measure its velocity, how its velocity and its height change as it goes up. So we can use either one of these experiments, but remember, in both cases, I'm still trying to figure out how my spring energy is related to this K and this delta X. So I'm going to have to do 2 separate experiments, but I'm still going to measure H in both cases. In one experiment, I'm going to vary my delta X. So in one experiment, I'm going to use a whole bunch of delta X's, just like we showed before. That should be a vector, of course. And I'm going to get some data this way. Another experiment I'm going to have to do, though, is to keep the same compression and try a bunch of different springs so that I can figure out how that energy, how that stored potential energy is related to K. We know it's directly proportional, but is it squared? Is it cubed? Is it linear? How are we going to find out? But in all cases, this part is not the definition of my spring energy. This is just my tool. This is just my measuring kit for figuring out what I need, right? So I can't put any kind of a spring energy meter on here, which would be ideal, right? If I could compress it and have it give me some sort of spring energy, that would be great. But I don't have an instrument that'll do that. But I can measure the height, and I know that that height is directly proportional to the spring energy. So I can figure it out if all I do is measure that. And this is how a lot of experiments will work. When you're designing an experiment, this is the kind of thought process you're going to go through. Now, this is pretty simple, it's pretty straightforward, but what if you're designing stealth composites and you want to tell how does this material respond under conditions of heat? How does it respond under conditions of being pinged by radar? How does it respond under conditions where it's in the upper atmosphere versus in the lower atmosphere? You're going to have all these variables involved. And so you've got to find some way of measuring something in order so that you can determine how it depends upon each of these variables. And that's what we're teaching you how to do here. Okay? All right. So for the rest of this one, since we could choose either one of them, let's go ahead and choose the altitude method, the gravitational potential energy method. The reason for that is because I don't have to do that separate graph, that x versus delta t, in order to get my velocity. I can read the height just by looking at my camera and seeing what my video camera and seeing what I get. All right. So we're going to use this expression here. Let's go to the next page. All right, so the relationship between the elastic potential energy, the mass, and the velocity of the projectile, this was the first way that we tried it. We said that the electric potential energy, the elastic potential energy was this. So that was our first attempt. And this is true. This will absolutely work. We could even use it as I'm coming up, but at that point, I don't have, let's say I'm using it as I'm coming up here. But here I've got more energy than just the kinetic energy, and so I would have to take that into account. All right. So here we're talking about now with our launch for microtest 4, we're using our cannon, and there's a spring in there, and we're launching that ball up until it gets here, and then it's at apogee. Okay. And so this is h, that's the height. All right, so where would it be at 0 then? We've discussed that. That's going to be at apogee. That's because the velocity is 0. So if the velocity is 0, the kinetic energy is 0. And so height is easier to measure. So that's where we've got our experiment. We did our sketch below, or I've drawn it over here, but let's just copy it into this blank so that we will have it. So your paper should look something like this. Just like we have over here. Okay. All right, now we need that mathematical expression that we worked out, and we said that because we have UGI, we have, I'll just repeat what we had on the previous screen, plus EKI is equal to UGF plus USF plus EKF. And then we go back through and we mark out everything that's zero. Well, initially, I didn't have any gravitational potential energy, and my projectile was stationary. Once I get to apogee, I don't have any more kinetic energy, and my spring is fully discharged, so that's gone. So all I'm left with is that US is equal to UGF, which is MGH, as we found last time. So there's my mathematical relationship in terms of this. Two different experiments, two different mathematical relationships, but both of them are going to give you the spring energy. You can't mix and match, though. Each equation goes with that particular experiment. The one in Microtask 3 is the one where we're launching just straight. All right, let's head on to the next page then. All right, so here's some data, and it's a little hard for you to read on the screen, but hopefully you have it printed out, or you've got it on your PDF on another screen or something, and you can zoom in so that you can see it. What we're wanting you to do with this page then is we want to have you convert all of these into our units. Remember, we want to have kilograms, meters, and seconds. So we've taken this data. We've done a bunch of different spring compressions, and then we have figured out the height that the projectile went in meters. Okay, so the first column then here, you need to convert all of these numbers into meters because they're given to you in millimeters. That's a little hard to read, but that's millimeters. I'll see if I can write this here for us. Now, this is minus 5 millimeters, and then it just goes up by 5. So 10, 15, 20, 25, 30, 35, 40, 45, and 50. Notice that it's negative. Are we compressing the spring, or are we stretching it? Well, the displacement is getting smaller, so we must be compressing, and that's what you would do with a spring cannon anyway. That makes sense. All right, so all we need to do then is convert that into meters. Well, that's easier than you think. That is 5e minus 3, because each meter, so I'll write it big here, 5e minus 3 meters. Because milli, so if I have millimeters, that means e minus 3. Millimeters, milli, literally means 10 to the minus 3. So if I have milligrams, that would be 1 times 10 to the minus 3 grams from here. So this is very easy to do. You just simply add that e minus 3. So my next column, my next row there would be 10e minus 3. Now if you wanted to write this out in kind of standard notation, this just means move that decimal 3 places this way. So for this one, that would be equal to negative 0.005 meters. You see I moved it 1, 2, 3. Same thing here, 1, 2, 3. This is going to be negative 0.010 meters. All right, now let's talk about this next one. Here we're wanting you to find the elastic potential energy from this height. All right, and these heights are not going to follow these regular ones, so you're going to want to look at your book or look at your zoomed in PDF so that you can actually see these numbers here. Then that's in meters, so we don't have to convert that. Then we need to find the elastic potential energy. Well, you might say, wait a minute, I don't have an equation for the elastic potential energy. How am I going to find that? What did we just talk about? We know that the spring energy, the elastic potential energy, is also, for this experiment, equal to mgh. It's not true all the time, but because of the way we set this experiment up, we get this simple result. And so that's part of the art of experiment design, is to make it so that you can keep it as simple as possible to measure the thing that you actually want. Okay, so all you need to do then is you're going to take the mass of the projectile, which we say is 0.5, and we'll go ahead and make, oh, sorry, it's 0.05. We're going to go ahead and make this to 2 significant digits. So that's going to be 0.050 kilograms. So that's my mass. We're going to use, for G, we're going to use 9.81 meters per second. And remember, it's not a vector because energy is a scalar. And then H, you're going to pull off of this column right here. So that's going to be very easy to do. Pause the video and do that. It's good practice to go through making these kind of data tables. It'll give you a good feel for what's going on. All right, well, once you've got that then, we want you to plot. Remember, we said our graph was going to be, we were going to plot the spring compression, which is delta x. That's from this first column. And we're going to plot that versus our spring energy, US. And so this is going to be in meters, and this then is going to be in joules, which is the unit of energy. So pause the video. Again, this one you're going to have to do in your book, or if you've got some extra graph paper, you can actually sketch it that way. Get a pretty good idea of what the shape of this curve is going to be like. It's going to be kind of important that we get it pretty much spot on. Pause the video, do that now. You got it? Because you're not going to understand the next part unless you've got something to look at. Okay, so we ended up with something that should have looked maybe, and I'm not being terribly careful in how I'm doing this, but it's going to look something similar to that. So it's going to be this curve that comes down. Nowhere is it straight. It's a curved line all the way throughout. All right. So that's our graph. Well, now we know, let's remind ourselves, we know that US depends upon K, and we know that it depends on delta X. But now we can see that that dependence is not linear. It's not going to be a straight line. There has to be some sort of power here. Well, how do we know which one? Well, to figure that out, go on to the next page. And actually, it's going to be the next page that looks like this. This page is just finishing that column. So it looks like this. So I'm going to advance 2 pages here. Here are some typical curves. So I'm going to go ahead and sketch what we had before over here for comparison. And we said that delta X, which was in meters, and US, which was in joules. And it came something like that. Right? And hopefully you've got a better graph here. So let's go through our library here. So this is linear. Is it linear? No. That's easily not the case. What about quadratic? You may say, well, does it have to do both? No, not necessarily. So if it's either one of these legs, it could be coming down this way. It doesn't even have to go to 0. It could be going this way or anywhere in between. Could it be that? It's possible. It's possible. So we'll keep that one for now. How about cubic? Now this one's a little tricky. You may say, well, sure, that one looks like the quadratic, doesn't it? But when it's negative, and remember our delta x was always negative, the cubic equation has to come up here. It has to come up this way. So in this case, since when delta x is negative, it was always compressed every single time, then my curve has to be able to come down this way. And the cubic equation doesn't do that. So if we were on the positive side, we would have a really hard time determining whether it was cubic or whether it was quadratic. And we'd have to look at it more closely to determine it. The cubic equation goes up much faster than the quadratic equation. So we'd have to make that comparison. But right now we can see that this cannot be cubic because the negative displacement should be coming up from the other direction. It should be coming up this way. Okay, inversely proportional, that means 1 over x. Well, here again, we've got the same thing. In the negative side, it's coming down like this. Well, that's curving the wrong way. It needs to curve the other direction. So it can't be that one either. All right, this is 1 over x squared. Now this one looks maybe a little bit more promising, but over here in the negative, do you see that it's going this way when we need it to go this way? So that can't be it either. So we're going to mark that one out. And then finally my square root. Now my square root cannot be negative, can it? You can't get a negative number out of the square root. So there is no negative part. So that one we can eliminate pretty quickly. So based on that, we can now say that we think that it is going to be quadratic. It's going to be to the power of 2 for our exponent. And like I said, you can actually, for something simple like this, there's a good chance that data graphing is going to come up with, recognize it. You could sit there and try different drop-down boxes, say, okay, is it linear? Is it exponential? All of that sort of thing. And then you're going to find that the one that fits it best is probably going to be quadratic. But you should also learn to recognize that in the data. Before you actually do any kind of fit, you should be able to look at that and say, oh, that's a quadratic. All right, so that's what we want you to learn with this. And you can keep this little reference library here, and I would make a card for these types so that you'll be able to recognize them each time. So put it in your flip book so that you've got it available. All right, putting our equation back up here then, We know that it depends on K, and we know that it depends on delta X, but now we know that it actually depends upon that displacement squared. Now it's not, this is, by the way, this is not the same as that. What this says is take xf squared minus xi squared. And that's not the same thing as xf minus xi whole thing squared. So be very careful with your notation here. They're not the same thing. All right, let's go ahead and get rid of this so that we don't get anybody confused. Okay, so far so good. So we're almost there. Take a look on the next page. Our next experiment then needs to be, how can we figure out K? We need to vary a bunch of different Ks. We're going to keep the spring compression the same every time. Always only vary one thing. All right, so go to the next page here. And here we have 3 different springs, or 4 different springs. Well, there's 4 here plus our original, right? So spring 1 was the one from the previous page, the one that you did. I'm not going to make you graph all of these, all right? So, but notice that the shape of the curve, is the exponent of that compression the same for all of them? Are all of them x squared? And by x here, I mean the horizontal component, which of course in this case is going to be k. Yeah, so the exponent of k, so the exponent in all cases is going to be squared. So they still vary based on x squared, no matter what we do. However, what's different is the amount that I get for the same amount of displacement from here. So here we've got the spring compression. I'm sorry, I wrote a k here. Whoops, let's make that. We're testing different k's. So this is going to be K1. Let's put it up here so we don't get confused. Or, well, I'm sorry, spring 2. So we'll call that K2, K3. This is K4, and this is K5. All right? Yeah, if we put it down here, you're going to get confused. This is actually my delta X. Okay? And so this is also delta X. And this is delta X. And this is delta X. And then once, because remember, that's what we're changing. The only thing we can change in this case is we're going to keep that the same for each one of them. All right, and then this is going to be my spring energy. Okay, that's a little easier to maintain. Okay, so now notice though that we get more energy if you zoom in on this so that you can see it. Remember, the compression is the same. For the same compression, I'm getting more stored energy out of it. So this must be the stiffest spring of these 4. And K1, which is our previous one, if you go back and look at it, it's even stiffer than this. We're getting even more energy out of it. See if that makes sense. Same amount of compression here. All right, so we've chosen a delta X here. And if you follow that up, you see that we actually go to a higher number than the same delta X right here. So that means K2, spring 2, has more energy stored in it than spring 3, even though they went to the same compression. So which of these must be stiffer? Of these 4, K2 is the stiffest, and then K3, K4, and K5. And then if you go back and compare it to your original one, you're going to find that spring 1, 2, 3, 4, and 5. So this is greatest, and this is least. And we're talking about the stiffness here. So for a given delta X, so if this is my delta X, you see I don't go as high as I do with this one over here. The number that I read off is actually quite a bit higher over here. Okay, you're going to need to zoom in on your book or the PDF to actually see those numbers. So pause the video and make sure that you see that. For the same delta X, for spring 2, for our K2 spring, we're actually getting more energy. It's going up to a higher stored US number than it is, for example, K5. All right, go through that, make sure that you see that, because that's what we're going to use here. All right, so then how did you arrive at your ranking? So we got more spring energy for the same delta X. same spring compression, that's what that is, for stiffer springs. And here we just used our physical knowledge. That stiffer spring we know is going to store more energy. Since K2 stored more energy, then that must be the one. So that still doesn't tell us though about the power. It does tell us that it's directly proportional, and so we guessed right. Right? Because as the stiffness goes up, as K goes up, I get more energy out of it. So they must be directly proportional. So this is correct, but it still doesn't tell us the power. So look on the next page. Here we've taken those 4 spring constants, and for those 4 stiffnesses. And what we want you to do is just read off the maximum off of each one of those graphs. So just pause the video. You just want to read off the maximum number. Just find the biggest dot, move over, read that value off. Pause the video, write that down now. Okay, so when I did this, when I measured it, I got 0.134 joules for spring 1. That was from your original one, from the previous exercise we were doing. For the first one on the page we just left, I got 321. It's frightfully difficult to write with this pen because you can't actually see where you're writing. So this is going to be 321 joules. This is going to be 0.710, and then I got 0.835, and then finally 1.318. So you see that as the stiffness goes up, which we said we were calling by K, the elastic potential energy also went up. So they are in fact directly proportional. But what's the power? So next I want you to stop the video, and for 1, 2, 3, 4, and 5, I want you to plot this maximum elastic potential energy that we got on the graph, and let's see where it comes out. Pause the video. Okay, you got it? It's only 5 points. Should be very straightforward for you to do. When I did this, I got something that looked like this. It was one that was up a little bit, so it wasn't a perfect line, but you should be able to see, switch to red here, that I have a linear fit to that. It's certainly not quadratic. It's not any of the others. The one that's going to fit it best is going to be that linear fit. And yeah, we're not exactly on there. That's because there's going to be noise in your data always. You know, maybe you didn't compress it to exactly the same distance each time. You just did it close. But we can see that that's going to be linear, where linear means to the first power. So since it's to the first power, then let's go to the next page. All right, so now we know everything that we need to be able to write our expression. So we know that the spring potential energy, so the elastic potential energy, is going to be directly proportional to the first power. It's going to be linear in K, but we also know that it's going to be squared in that spring compression because it was quadratic, right? So as I increase my delta x, it's delta x squared that's going to determine this maximum US. However, the K part, as my stiffness of my spring goes up, my elastic potential energy goes up at exactly the same speed, at exactly the same rate. So if I double the spring constant, I'm going to get twice as much energy out of it. However, with the delta x, that's not true, right? If I double that, I'm actually going to get 4 times as much energy stored, all right? Because it's to the second power here. Now there's one last little wrinkle here that we want to talk about. We know that we always have this constant here, this constant of proportionality C. We need to know what that is, but our experiment didn't give that to us, right? There was no reason why we had to have it be anything other than 1, right? We could absolutely just define that to be 1, and it's going to work. It's going to match all of our observations, and we're done. Traditionally, though, we define the spring constant to be twice what we would get experimentally. And you may say, why the heck would I want to do that? Well, because if it's twice that, if the K I define is twice that, then I'm actually, when I write my equation, I'm going to have a 1/2 to bring it down to what it really is that I found through experiment. Does that make sense? Let's go through that again. If the K that I write down, let's say I look up the K for a spring, and let's say, making up these numbers, let's say that it was 100. We're not talking about the units just yet. Well, in order for it to match this equation, this is what's published. But really, if I do the experiment, it's going to come out as though K were 50 from that. So what I'm going to do then is, since this is what the dealers are going to sell me, if I go out to buy this part or whatever, then my equation becomes 1/2 of whatever the dealers were saying it was from that. And you may say, well, why on earth would I want to do that? Because sometimes I'm going to end up having to take a derivative. So if I take the derivative of u with respect to x, with this case, 2 times 1/2 is just 1, and I just get k delta x. And that's nice and simple. On the other hand, if I had us equals k delta x squared, and I used what it really is, then when I take my derivative, my du dx, we've got to put our s here just to make sure we're not confused, then that ends up being 2k delta x when I take that derivative. So why would I want to carry around this 2? Because after all, this is just a number. K is a number. It doesn't change. It's just a constant for that particular spring. So since it's a constant, I may as well define it in such a way that makes my job easier, because we are lazy. So traditionally then, this expression that we have up here is going to be our expression for our elastic potential energy. It's going to be 1/2 K, and that's the spring compression squared. Now, what happens if I stretch the spring? Now my spring is not compressed, it's stretched, so my delta x is positive. Take a look though, when I square that, I'm going to get exactly the same number that I would have gotten if I had my spring, if I had it compressed. So stretching it the same distance stores just as much energy as compressing it that distance. And that's something that that equation is telling us right now. If we had something like this, thinking it was linear, right? Then this would come out to be a negative number. But wait a minute, we've got a problem here. This is a vector. Energy is a scalar. So I would need to have some other vector in here, but K is not a vector. It's just a number, it's a scalar. So this equation doesn't work. However, if I have this equation, I'm going to write out my two vectors. It's delta x dotted into delta x. So that's the scalar product of two vectors. The scalar product of two vectors is, duh, a scalar, right? So this number right here, I can actually get rid of my vector sign because it's just a scalar at this point. Can you see that? Because it doesn't matter if I compress it or if I stretch it. I get exactly the same thing, as I must, because it's going to be a scalar. So I'm going to get rid of this, even though, yes, my compression is in fact going to be in a direction. Notice though that if I take the derivative over here, when I took the derivative, I ended up with something that should end up being a vector, right? So, because I'm going to have just my regular delta x there. For the energy though, it's a scalar. So, since I took the dot product here, then that completely goes away. All right, so this then is going to be our final form for our elastic potential energy. So you're going to end up making yourself a flipbook card based on that. So the last thing we need to do then is just figure out the units. And we started this before. We know that energy is kilogram meter squared per second squared. And now I know that's my energy, that's my US. Now I know that I have K times meters squared, right? Because that's what this is. So that tells me that K then must have units of kilogram per second squared. And that may not seem like anything reasonable. Oops, not kilograms. Because we know that it doesn't depend upon time. But eventually we're going to introduce a unit called the Newton. And that's going to take care of this. And that's going to give us something that makes a lot more sense when it comes to that. Okay, so there's one more thing I want to talk about before we move away from energy and start introducing the concept of forces, which we'll be talking about next time. People tend to confuse the concepts of power and energy. They may say, well, how much power are you using? Well, that doesn't actually make sense when it comes down to it. So power, if you look on this last page, it's the rate at which energy is being used or generated. So the rate at which it's changing from that. So in this last microtask here, let's see if we can figure out an equation for power, because once we have that equation, hey, we can actually do some more calculations with that. So we use the symbol P to be power. Now this is a capital P, a little hard to tell, but it is a capital P. Now, because it's a scalar, there's no vector sign. So just like energy is a scalar. And we define that to be the rate of change. And of course, that's the rate of change of energy with respect to time from this. So that is the definition of power. And so you should be making a flipbook page for this. So energy, what are the units of energy? Well, it's the joule, right? So power has units of joules divided by time, and the energy units of time are what? Seconds. So the fundamental units here that we're going to be talking about are going to be joule per second. Now the SI unit for that is the watt, because I'm just a joule every second, but you knew that, right? So, and then we use a W, to a capital W, to represent the unit abbreviation for that. So you've probably heard of a 10-watt light bulb. A 10-watt light bulb or a 50-watt light bulb or a 100-watt light bulb or whatever you're using, that's not a measure of energy. That's a measure at how fast it's using energy. So if I have a 100-watt light bulb, then that means it's using 100 joules of energy every second. So if you run this for 60 seconds, well, then you've used 60 times 100 or 6,000 joules of energy, which is actually quite a lot when it comes down to it. So we can use this then to actually do some calculations. So take a look at Microtask 13, and it says we've got a gallon of gasoline has about it's a little hard to read on there, so I'm going to read it here. It's 1.4 times 10 to the 8th joules of energy. So let me get rid of this so that we've got some room. Okay, so the energy contained in that, and it's actually going to be a stored energy, right? It's going to be a chemical energy, and that's going to be 1.4 times 10 to the 8th joules. Now, we generally will write this scientific notation using engineering notation. So we will say 1.4 E8 joules. Now, or you could do positive 8, but we'll just say E8. And that's going to be the energy that's stored in there. Now, this is stored as chemical energy, so we could actually use this symbol for it. U is potential or stored energy, and then C with little subscript says that it's chemical. For now, we're just interested in the total energy that we're going to put back up in here. All right, so a typical small car burns about 2 gallons of gas for every hour of its operation. So we want to know how much power does the car's engine produce. So that's how much energy per second it's producing from that. Well, we have to think about that. So we need 2 gallons. This is per gallon, right? And we have 2 gallons of gas. So we're going to think about our units here. I need to get rid of my gallons here. Let's write it out here as a fraction. So my energy is 1.4 E8 joules in 1 gallon. Well, we have 2 gallons. So that's going to get rid of that. Now, what I want for power, though, is I want the energy divided by the time. So in order to get, so this is my E, and then in order to get my power, then I have to take my change in energy. So if let's assume I burn all this up so that it goes from 1.8 times 10 to the 8th times 2 down to nothing, so that we use all of it from there. So it does that in every hour. But what units does my time have to be in? It has to be in seconds. So what we can say then is this is going to be 1.8 times 10 to the 8th joules times 2. So I can use that to figure out my total here. And then divide that by my time in seconds. Let's set that up as an equation. So my power is my energy usage per gallon times the number of gallons. E here is the energy per gallon, just like we've got right here. And then I need to, so that's my total energy. So it's going to be 1.4 times 10 to the 8th times 2. And that gives me joules. So that's got units of joules. And then I need to divide by the time. Well, we said that we've got 1 hour, right? Well, how many seconds are in an hour? You might just know. But let's pretend that we didn't. I know that there are 60 minutes in 1 hour. You see, now my hours cancel. I'm left with minutes. Well, I need to get rid of that minutes and make it into a second. Well, of course, there are 60 seconds in 1 minute. And now my units cancel. So now I'm left with units of joules per second, which is, in fact, watts. So by looking with the units, even if I don't have a specific equation to give me what I want. It's an equation, sure, but it's just by definition. So I can look at my units and arrange my units so that everything cancels out the way I want it to be. So if we're going to put this then and plug in our numbers, let's get some room up here where we can do that. And we'll just clear this out right here. Okay, so now we're going to put in our numbers here. So my power then is going to be equal to the energy per gallon, which is 1.4 times 10 to the 8th. And we're going to put our units in here, joules per gallon. So now it becomes pretty obvious. Times, I have 2 gallons. And you see that my gallons are going to be canceling, and I'm left with joules. And then it burns that in 1 hour. And we decided that that is 60 minutes in 1 hour and 60 seconds in 1 minute. So those cancel, those cancel. And so now all I have to do is multiply everything in the top, divide by everything in the bottom, and I'm going to be done. And so if I do that, then you're going to see that you get, when I did this, I got 77,800 watts. And if I want to write that in engineering notation, then that would be 77.8 kilowatts from that. I usually write K with a lowercase letter, so let's do that. So 77.8 kilowatts. That's how much energy a typical small car is going to produce. All right, so the next one says a typical small engine private aircraft then will burn the same amount of gasoline, about 1.4 times 10 to the 8th joules, in about 2 seconds. So we want to know how much power does the aircraft engine generate. Well, we've got the same issue. We just need to make sure that our units work. So I want to know the power. I know that it's 1.4 times 10 to the 8th joules per gallon. Okay. And again, we have 2 gallons because we were told it was the same amount of gasoline. So the reason I know that, gallons cancel, I need joules on the top. That's good. Now, in the bottom, though, we don't want to just divide by this 3,600, 60 times 60. You look at the problem carefully, and it says that it does that in 2 seconds. So that's what we have right here, the 2 seconds. Well, that's already in units of seconds, so I'll just divide by 2 seconds. And you see that I'm left checking my units. The gallons go away. I'm left with joules per second. So I don't need to do any other conversions on this last part. And when you work that out, you're going to find that you get about 1.4 times 10 to the 8th watts, which is equal to about 140 megawatts, which is a lot. So you can see that that aircraft engine has to produce a lot more power than the car engine. And that makes sense, right? Because we've got to give it some potential energy in addition to just the kinetic energy that it needs going in there. So we would expect that that's going to produce a lot more power. The flip side of that is you're going to burn a lot more gas because the energy content in the gas is the same. Both the aircraft and the car is burning the same amount of energy. The aircraft does it in 2 hours, whereas the aircraft does it in 2 seconds, whereas the car does it in 2 hours. But the total energy used is still going to be that 2.8 times 10 to the 8th, 2 times 1.4 times 10 to the 8th joules. However, you don't get it for very long with the aircraft. So that means that my total power usage is going to be a whole lot higher. So now you have pretty much all of the techniques that you need to work with energy in the energy method. Remember that the big advantage to energy is that it's a scalar. It's not a vector. So I don't have to worry about a lot of the things that I would if I were working with vectors. So it's just a change. So I can have my roller coaster route. I can find out my velocity at any point simply by subtracting these 2 scalars from each other and maintaining my conservation of energy. Now we've only talked about 3 kinds of energy so far. We've talked about kinetic energy, gravitational potential energy, and elastic potential energy. But the techniques that we've developed here apply to any form of energy that you can possibly think of. So you've learned the tricks that you need, and now we can do that with any other kind of energy that you might want to work with. In the next series of lectures, we're going to introduce the idea of forces. And forces relate to work. And remember that work is what we need to change an energy. So everything that you've learned in these concepts are going to apply to this material that we're going to talk about starting next time when we start talking about the force that's required to change an object's motion. We'll see you next time.